Okay, this is 8G6, 8th grade geometry, standard 6, video 2, the Pythagorean theorem, its proof, and the converse. A few terms to know. I'd like you to copy these down in your journals and define them. All right, what I've done here is I've located some history on Pythagoras, and if you'd like to pause the video and read through, you don't have to copy this down, but read through it, find out a little bit about Pythagoras, because we're going to be dealing with his theorem a lot. I thought it'd be a little nice to have some background information on Pythagoras here. All right, so the theorem is stated as a squared plus b squared equals c squared. We have some variables here. We've talked about what the exponent 2 means, and let's just kind of figure out what the triangle looks like and place some of these variables where they belong. Special note that this theorem will only work with 90-degree right triangles, so it's important for me right now to put in that box. That box is important because knowing where that angle is, it tells me where the most important leg is. And the most important leg is known as C. And from your terms, C is known as the hypotenuse, and it is that slanted line that is directly across from your 90-degree box. So important to find the box, and then more important to locate the hypotenuse, because the hypotenuse will never change. It will never be altered. C will always be that slanted line across from the box. Now, A and B actually are interchangeable, believe it or not. Even though they're different variables, A and B, B can be on the base. Normally we represent B as the bottom or the base. But according to the theorem, since we are adding the two values together, that would be a part of the commutative property, because let's just say an example, A is 9 and B is 16. Well, 9 plus 16 is the same as saying 16 plus 9. So that's why these numbers or variables are interchangeable. So, go back on that one. We can actually just take this and flip it around. All right, but who's the most important? C is not interchangeable. All right, now the proof. So the standard states that we need to have a proof of this theorem. So given specific dimensions of these right triangles, why does the theorem work? All right, let's draw in our 90-degree angle if it's not given to you. And we're told that it's a right triangle, I like to draw it in. And what that has done is it's created on this grid paper certain dimensions or lengths of each leg. And if I'm going to take the vertical leg going straight up and down, I'm going to count the units here. So I see 1, 2, 3 units. So if it's a square, right, a squared, a to the second power, I'm going to create a 3 units by 3 units square. So if I come down 3 units, I'm going to go across 3 units to here, and then I'm going to go up 3 units to here, and then I can come across again, and I have this 9-unit box. So why don't I just try to find one of those? I think this is the 9-unit box. And there is your a squared. Let's change that color a little bit. So underneath, can you see all 9 of those squares that are covered? All right, then the theorem says we're going to take the B leg and square it. So let's count the units on the B leg. Coming across horizontally, we have 1, 2, 3, 4. So we're going to create a square out of that. Coming down 1, 2, 3, 4. And it's going to look like this. And underneath, how many boxes do you think you're going to see if you have a 4-unit square? Okay, 4 times 4 is 16. All right, now according to the theorem, we're going to take the a square and add it to the b square, and that's going to create this c square. Now, how many units are going to be under that particular box? Well, we're going to have to kind of play around with that a little bit. We could put the numbers into the theorem and solve it, which we're going to actually do later on. But if I'm going to have a proof, I'm going to take this ended up being the b square, and I'm going to rotate it and put it right on top of the hypotenuse leg and see what happens. Okay, well, when I put it right next to it, you're going to notice that we have some missing pieces. I have this missing piece that's right over here. I did not create a square, and if I added that piece on, I think we're going to even end up with a rectangle, and we can't have a rectangle because it's supposed to be a square. And some teachers like to use paper. You know, they'll take out some paper and they'll have the students cut the paper up into the dimensions to create this square. I think since we're on this Promethean board, we can play around with this last piece here. Now, if I were to try to fill in the remaining pieces, I probably need to know how many squares should be covered. All right, so I'm going to do the math here. So if I have 3 squared, which is 9, and 4 squared, which is 16, what is that going to equal when it comes to c squared? Well, I have 9 plus 16 is 25, and 25 is equal to that c squared, and we've worked with the square roots. So if c squared is 25, that means I'm going to have a 5 unit by 5 unit box. So I'm going to have 25 squares covered. Well, right here, we've only got 16. Now I'm going to have to manipulate this remaining 9 so that it will fit. All right, well, what can I do? I need to add the 5th unit on this side and drag it. What do we have here? This is a 4 by 4, so 1, 2, 3, 4. I'm going to need the 5th unit, right? Because it needs to be a 5 by 5, and I know that this purple box was only 4 units long. So I'm going to extend this. So I'm going to take this 9 unit box, I'm going to shrink it. I'm going to take 3 off. I'm going to take another 3 off. So I've just subtracted 6 from my 9, and then I'm going to extend it. Well, right now it's 3. I'm going to add another unit, which is 4, and I know I need a 5 by 5 box, so I'm going to extend it that 5th unit. Let's make sure that we're accurate here. All right, now when I take this and apply it to my c squared, you're going to notice that it went a little long, okay, because I needed to create a 5 by 5, and the purple, like I mentioned, was a 4 by 4. Well, what do you think we're going to have to do to make this into a square? You're right. We're going to have to add back those remaining pieces of our 9 square box. So if I have 5, I'm going to have to create one of these rectangles that is only 4 units long. So let's go into the shape box, and what kind of colors do we have going here? Well, that's not going to work. How about this? So we took 4 away, right? We have a 5-unit yellow rectangle. Now we took 4 away from the 9, so we're going to have to add those 4 back. So 1, 2, 3, 4. And then try to line it up here as best as we can. And we now have the 5 units by 5 units square. And underneath that square, believe it or not, there are 25 of them. You can't really tell because there are all these little pieces. It was easy to tell in the yellow and the purple one, but when we put it over here on the hypotenuse, all these little wedges actually add up to 25. And that's what the theorem helps us to do. Okay, that was the proof. The converse of the theorem, this is going to be proving whether or not triangles are right triangles. And it's basic substitution and checking the math on them. All right, so basically it says the converse states that whenever the sum of the squares of the two sides are equal to the square of the third side of the triangle, this triangle is known to be a right triangle. So again, substitute and check. If the left side is equal to the right side, it is a right triangle. If they are not equivalent to each other, it's just a regular triangle. You know, it's not a 90-degree triangle. All right, so let's check here. We're going to label first all of the legs, and it's important to know that the longest leg is always the hypotenuse. So locate your C value, and 5 is the longest. So I'm going to label that as C, and then, you know, A and B are interchangeable. I can just call that A and B. But you need to find C first so we know what numbers to plug in the correct areas. So if A squared, we have 4 squared plus B squared is equal to C squared, that's our C. Let's see if that actually is true. Well, 4 squared is 16, and 9, and that's what, 25. 16 plus 9 is 25. Okay, so since the left side is equal to the right side, I would say yes, this is a right triangle. Get that out of our way. All right, the second one. Let's see if this one's a right triangle. So my C is 10 because it's the longest, and A and B are interchangeable. So we have 6 squared plus 8 squared. Is that equal to 10 squared? All right, 36 plus 64, and that is 100. 36 plus 64, let's see, do the math. Okay, that's 100. So once again, yes, these 3 lengths do in fact equate to a right triangle. All right, one more. Locate your hypotenuse. Your hypotenuse is the longest leg, which is 9. We'll call that C, and A and B are interchangeable. All right, so we have 7 squared plus 8 squared. Is that equal to our 9 squared? All right, so 49 plus 64, is that equal to 81? All right, well, let's do the math. No calculators, so 64 plus 49. 9 plus 4, carry the 1, 6, 10, 11. Okay, so is 113 equal to 81? No, they are not equal, so you would say no, this is not a right triangle. And this is using the converse. It's taking 3 lengths, plugging them into the theorem, and checking them. All right, today we talked about proving the Pythagorean theorem. We also discussed checking dimensions to see if a triangle is a right triangle. In the next section, we are going to be finding the missing legs of right triangles by using the theorem. Okay, please define the given terms on page 2 of the flip chart and write a few sentences on what you learned today. And if you have any questions, bring those questions to class with you.